try to explain to you our ambitious project to create an hub here in Giuliano. To let people perceive our mood, we choose a Charles Leader saying, in the past you were what you owned, now you are what you share. So this is social innovation to us. Up to now, knowledge and research have been made inside universities and factories, and only a few times these two realities meet each other. The survey appears many-sided than we could imagine. So nowadays, innovations is released all over the world, and the role of innovators is to concur to research not only from a well-defined place, but everywhere. So the hub will foster people to get in touch with these realities and to join them. The crowdfunding, it is receiving renewed attention from both commercial and social entrepreneurs. Now that social media, online communities, and micropayment technology make it straightforward to engage and secure donations from a group of potentially interested supporters at a very low cost. So it is the way we imagine to make social innovation happen. It is based on the community, involving people to share innovations, ideas, and decided for funding new startups. So how the work idea has changed. In a time of economical and work crisis, people decide to share costs and to join together. So actually there are 1,320 co-working places in the world. Okay, here you can see the increase in few years of the co-working places in the world. These co-working places were born with more than 400 different names, and here you can see some of them, like Co-worker, Independence of Philadelphia, and so on. All these labels belong to a scene, social innovation networking. This is another slide telling us there are 40 hubs in the world at the moment. So, Hub Napoli North. The metropolitan area of Naples is the second largest city in Italy after Milan. This metropolitan area is one of the most populous in Europe. The city of Giuliano is the second largest city in Campania after Naples by extension and by population. And here you have some extra information about Giuliano. You have to know that Giuliano is really close to the city of Aversa, where there are two universities, engineering and architecture. And the underground and the railway station are really nearby, so it's really well linked. The Palumbo Palace. So, the Palumbo Palace is dated back to the Middle Age, when the building had a crucial public role. It represented the feudal ownership. Subsequently, it was used as government seat, and during the Giambattista Basile's period, who was the governor, the palace was also used to administer justice. Here you have the roof that we saw before, and the west side and the other side. This is just the disposal at the room at our disposal. So workspace usually refers to premises provided to help new businesses to establish themselves. These typically provide not only physical spaces and utilities, but also services and links and contacts to support and finance innovative ideas. We already have a clear idea about the hub layout because it could be the first test for Business Hub Incubator, because we will use the link with Camerino University that is working on this kind of project. This innovative project, led by Professor. This is the disposal of the desk. This is the slide I was just talking before. It is called the mobile arc. Yeah, because it provides further desks just by lifting or pulling down chairs and desks. So this is the how we imagine the use of the desks, but it's still a work in progress idea. So we have thought of a pyramid made of people or hub members that decreases as you go up. So at the basis level, which is a really crowded one, we put socialization. So we've planned a lot of activities to attract a large amount of people to the hub that usually wouldn't come here. So I'm talking about a series of social events like tango lessons, English courses, or photography or picture courses. So they will become a tool to bring new potential hubbers into the hub. So next step is a network. That is to say, you will reach with the basis card, you will reach the internet and you will be involved in all hub activities. Then you find the co-working. So if you decide on hiring your desk monthly or yearly, you will be your workspace, and you will even reach all the hub contacts and links that will be useful for your work. Then there is education on demand for people or factories, and then you find you will find the incubator, that is the main level of the hub. That is to say, the crowdfunding for startups or social innovations. So will be the foundation of the society, the advertising events, and then the opening on September. Okay, we're finished.
Roberto Germano di PROMETE, vi presento Elmar Fuchs e Adam Wexler del centro WETSUS, che è il centro olandese per la sostenibilità delle acque. È un centro di eccellenza che non ha soltanto scopi di tipo scientifico, ma anche grossi interessi in relazionarsi alle imprese per progetti comuni.
I would like to use this opportunity to thank the organizers, especially Roberto and Emilio, very much for inviting us here, for giving us, both Adam and me, the possibility to present a bit of our latest research here in our presentation, which is called A New State of Water and Other Electrohydrodynamic Bridges. This is a talk about the interaction of electricity and water. And before I go to the experiment, I want you to remember that although this is a lab experiment, actually electricity and water work together in the nature all the time around us. It's high voltage, and water is the basis of what is responsible for thunderstorms, what creates weather, and most likely is also responsible for the creation of life some long time ago. Not so long ago, a little bit more than 100 years, the experiment that we are going to talk about was first found, and it was discovered by Sir William George Armstrong, and please let me quote from this paper which was published in 1893, because it's always nice to hear the discoverer in his own words. And he says, amongst other experiments, I hit upon a very remarkable one. Taking 2 wine glasses filled to the brim with chemically pure water, I connected the 2 glasses by a cotton thread coiled up in one glass and having its shorter end dipped into the other glass. On turning on the current, which at that time was a steam-driven Van de Graaff generator, on turning on the current, the coiled thread was rapidly drawn out of the glass containing it, and the whole thread deposited into the other, leaving, and this is important, leaving for a few seconds a rope of water suspended between the lips of the 2 glasses. So that you can more easily imagine what this looks like. We have 2 glasses here, we have a cotton thread. We turn on our current, and as you see, there's actually a bridge of water forming around this thread. However, nowadays, when we run this experiment, we don't use a cotton thread, we just use 2 beakers, fill them with deionized water, put 2 electrodes in there, and we apply high voltage, 15 kilovolts direct current. And for most of the experiments, we use a constant current of 0.5 milliamps. Now, if you switch on the current, a watery connection forms. And more than that, if you take the balances, you will also see that there's water being transported. However, enough of these sketches, let's have a look at the real thing. What you see here is a slow motion video of the formation of this water bridge. You have the 2 beakers, the electrodes are just outside of the frame, and you see that at a certain point there's a discharge. The water is moving wildly in both beakers, droplets are ejected, water columns are formed, and interestingly, the water tries to form a connection. It tries to get in touch with each other. You see here the water is trying to flow upwards on both sides. And please remember, this is slow motion factor 120, so in real time this is much faster. And after some time, we have here 2 droplets sitting on the edges of the beakers, ejecting in a pulsating mode, and at a certain point, they will form a very thin connection. This is a capillary bridge, this is not a water bridge. Until this point, the phenomenon is very well understood. But now suddenly, once you have a very small connection, the phenomenon gets suddenly much thicker, more robust. You see water flowing through, and suddenly you have a real macroscopic phenomenon. You have a watery connection between 2 beakers. And more than that, this is a real-time video, so it's very fast. Now the connection is formed. More than that, if you're now to pull one of the beakers away from the other one, this connection actually remains stable and forms a floating cylinder of water. To give you an idea about the size of all of this, the diameter of the bridge is 3 to 4 millimeters here, and its length will be, in this video, about 25 millimeters. Moreover, you see that this is not a rigid phenomenon. It's not like an ice bridge. It's moving rapidly. You see with the naked eye oscillations in the diameter. If you take other techniques like laser schlieren, for example, you would also see that there are dynamics which are much, much faster happening inside of the bridge. And moreover, you see that the level in one beaker goes down and the level in the other beaker goes up. So even from this crude observation, you see that water is being transported through this floating bridge of water. So please remember, this is just electricity and water, nothing else. Well, it would be interesting to know, since we have seen that the levels in the beakers go up and down, how is the water actually flowing through this bridge? In order to take a look at that, we added tracer particles, polyamide inert tracer particles, and again took a video with a high-speed camera. And as you can see in this video, these particles are circling, which means that, at least on the outside, the water is not flowing straight, no. It's spiraling around the bridge. And this is only part of the truth with a new technique, which we recently got at WETSUS, thermography. Actually, it's high-speed thermography. This is a technique where you see the infrared emission. So actually here, what is bright is warm, or high infrared emission, and what is dark is low infrared emission. You see that the actual activity, the actual dynamics of the water seems even more complicated. And if you take a closer look at this is the water bridge in a high-speed thermography video. You see it's not just circling, there are vortices which are moving across the whole phenomenon. I'm an astronomer as a hobby, and this always reminded me of the clouds of Jupiter. So it looks as if there's a whole, this whole dynamics that's going on is even more complicated than we originally thought. It's not just spirals, it's a very, very complex situation of dynamics going on here. Now, how do we explain all this? Well, from a static approximation, it's actually very simple. Because you have to think, what is the reason that keeps the bridge in place? Why doesn't it fall down? Well, you can easily simulate the electric field, as you can see in this graph. And we know from basic physics that there is a force from lower field strength to higher field strength. So we have a force that pulls the water out from the beakers and also from the bridge back into the other beaker. It's true for both sides. And even more, whenever the bridge wants to break down, electric force is created that will move the water back up into the horizontal position. So from a very static, simple approximations, there are no questions. However, this is just a crude approximation of the whole phenomenon. And we have not understood the dynamics. And, well, one of the biggest questions that were asked since the rediscovery of this phenomenon was, first, is this bridge intrinsic to water? So is it only possible with water, or do other liquids do this as well? And even more important, is this just a purely macroscopic phenomenon, like you also have a vertical bridge when you turn on the water that's running down? So is this just macroscopic, or is the water in this bridge different on a microscopic level? And the answer to that, both of these questions will be given by my colleague Adam Wexler.
Well, this is indeed a very interesting question. To what extent are the properties of a material reflective of the collective ensemble, and to what extent are those properties derived from the individual components and their interaction? So in water, this is actually a very, very difficult question to answer. In fact, in all liquids, this is a difficult question to answer, because liquids move very quickly, and they have very, very fine structure. So oftentimes when I'm explaining this question to people, I refer back to the human population. I say, how can you describe all of the people of the world with one simple statement? People often scratch their head and think, well, that's difficult, actually, because every individual person is slightly different, and it's our collective movement together that creates this emergent phenomenon of the human population. So when studying this phenomenon of the water bridge, we were very curious, is this really just a collective bulk property? Is this just something that can exist because of a dielectric constant, the ability of an electric field to form inside the material? Or is there something more individual happening within the bridge? So there's a new technique that has been around now for about 10 years, and it's called ultra-fast vibrational spectroscopy. And essentially, what we do is we use very high intensity, very short laser pulses to excite water molecules from a ground state into an excited state. And when we do this, their absorption cross-section, their ability to absorb the infrared light that we use changes. And what this allows us to do is it allows us to measure how the water molecules are communicating with each other, how they are interacting with each other. And we can do this essentially in real time for a water molecule. And real time for a water molecule is a very different time scale than you or I are accustomed to. Most of the fluctuations within a water network are occurring on the order of picoseconds. And a picosecond is about 10 to the minus 12 seconds. And these vibrational modes that we excite are happening on the order of femtoseconds. It's 10 to the minus 15 seconds. So we use a couple tricks. In spectroscopy, you have to create contrast. And one of the ways that we create contrast in water is to use deuterium. Heavy water is slightly different in the way it behaves compared to regular light water. Because heavy water has an extra neutron in its hydrogen, deuterium. The vibrational frequency is different. It's slower. It's a lower tone, if you will. And so we can differentiate, thus, between normal water and this heavy water. It allows us to sort of just tag a few people in the population, if you will. Now, what do we know about how water behaves? In ice versus liquid water, this tone of the deuterium tagged water is different because in ice, the water molecules are very tightly bound to each other. They're organized in a crystalline structure. It would be as if you took a room full of 100 people and you put them on a very regular lattice and said, okay, everyone hold hands. And then you went to one person and you asked them to move. They would have a difficult time doing that because they were linked to everyone else. Similar way, in liquid water, you have a few people holding hands, a few people dancing, a few people just standing by the wall, maybe someone at the bar. As a result, if you ask any one of them to move, to change a position, it's actually pretty easy. So we can see this spectroscopically. And essentially what we find is that when we excite water molecules in a solid phase, in ice, they stop ringing if they were a bell. They would stop ringing much faster than they do in liquid water. And what we can do is, like I said, we can actually measure the time of this ring down. We can measure how quickly we change from an excited state back to a ground state. In liquid water, we wind up with a time of about 740, 750 femtoseconds, 10 to the minus 15 seconds. And in ice, it's much, much faster, 385, 390 femtoseconds. Now note that this is a phase transition. So the temperature is the same. It's 0 degrees. So thermodynamically, essentially, the motion within the system can be averaged to be the same. And this phase transition forms what's known as a no man's land. I want you to remember that. So here's a little cartoon that we created to try and show you what it is I've just been talking about. So we see here these little red spheres are hydrogen. The blue spheres we can consider oxygen centers. On the left-hand side, we have the liquid state, where, like I said, there's not so much coordination. All the molecules are not holding hands at the same time. Whereas on the right-hand panel, we have the solid state, and there's very strong correlation between water molecules. So we use an infrared laser beam, we excite the vibrational mode, the stretching mode between the oxygen and the hydrogen, and you can see that in the liquid, it persists a little bit longer. It doesn't ring down as quickly. So there was a question. In the water bridge, we see this strange phenomenon, right? We see water essentially spanning a gap against the force of gravity. How is that happening? Is it purely, as Elmar had said, just the pressure? Or is there something else going on? So using this laser technique, we were able to measure the speed of relaxation in the water bridge versus normal bulk water. And what we found was indeed that the water bridge rings down much more quickly, that the molecules are indeed more tightly coupled to their nearest neighbor. This is important because it says that this phenomenon is arising from the molecular level, that there are changes at the individual molecular level that are resulting in this macroscopic phenomenon. Here's another look. I had shown you that graph where I showed water and liquid water and ice at 0 degrees C. And actually that's what that vertical line is right there, essentially. So we have temperature, and we have the relaxation time, this time in picoseconds. But I want you to know that there's that no man's land. There's a jump discontinuity, is what we like to call it, where essentially when you transition from one phase to the other, the time jumps. There is no intermediate value. The water bridge lives in this intermediate range. It occurs that the relaxation time of about 600 femtoseconds is between these two values for liquid water and for ice. Furthermore, this is occurring, as Elmar showed, somewhere between 25 degrees C and 40 degrees C. So not only are we in a liquid state or a quasi-liquid state that has a very different relaxation time, but we're at a temperature where we shouldn't see this time at all. I mean, you could see the difference between liquid water, ordinary liquid water at 40 degrees C, and the water bridge is almost 200 femtoseconds. That's a significant difference. Now, all good scientific questions always center around a paradox. And so now I invite you to join me in thinking about this one. While we can measure the relaxation time of the water molecules, we can measure also their ability to transmit the information, the energy throughout the whole network at the same time. We call this thermalization, which is essentially the slow redistribution of that excited energy. If I take one person in this room and I shake your hand, I give you a bunch of coffee, you know, I get you very excited, maybe you run around a bit, you bump into a few people and you slowly calm down. But does that energy, how does that energy move through the group? How does it distribute? Do more people get excited? And how long does that take? Well, we could also measure that with the water bridge using the same laser technique. And what we found was, unlike the relaxation time, the thermalization, the spread of that energy, was much, much slower. 7, 8 times slower. We can see on the far right-hand side, there's 2 triangles. One of them is in black. That's the thermalization time for ordinary bulk water, which is about 250 femtoseconds. And we see the blue triangle up towards the top, which is the thermalization time for the water bridge. And this is about 1.5 picoseconds. So you're talking quite a big difference again. But these are sort of opposite effects. On one hand, we're saying water molecules are very tightly bound to their nearest neighbor. But on the other hand, we're saying somehow, for some reason, this excited state lives longer within small populations. In other words, it's as if there are small groups within the room, and we can excite a few people in one group, but that excitement doesn't leave that group and enter the rest of the room for quite some time. So this is paradoxical. The main reason is that we always think about water as a continuous network. It says, we say water is connected. You know, you really can't say where one water molecule on that side of the room ends and another water molecule on the other side of the room begins. So just to summarize, we see here's this jump in the relaxation time for the OH stretch, the phase transition, the no man's land, the water bridge at 25 degrees C versus ice or liquid water at 0 degrees C. So we're definitely in a new state. This is not something that's known. This is totally a new state of water. And furthermore, we find that the thermalization, the redistribution of this energy, is vastly different. So there seems to be a paradox. Yes. And so we ask now, what could this new state be? Well, as Elmar had said, we live in a world of electricity and water. And actually, it is our very living systems that are perhaps the best example of electricity and water forming something useful in the natural world. So the water bridge, just for comparison, has an electric field of about 10 kilovolts per centimeter. Research done at the University of Michigan, the Koppelman Laboratory, where they looked at human neurons using photonically active nanoprobes for voltage nanoprobes, which basically allow them to measure the electric fields inside living cells with spatial resolution, so they could say near a mitochondrion versus near the nucleus, I can differentiate the electric fields. They found in living cells 50 to 300 kilovolts per centimeter electric field strength. This is a significantly higher strength than we have in the bridge even. So if at 10 kilovolts per centimeter in pure water, I can create a new state of water, the question really becomes, what's happening inside our cells? What's happening within biological material? And how does it relate to the extreme sensitivity and the robustness of biological life? Back to the hardcore science, more questions. One of the things we wanted to know was, in the water bridge, are there changes in the bulk properties as well? So we use a technique called inelastic UV scattering, which essentially is a direct measure of certain properties like the propagation speed of sound, and also certain kinematic viscosity terms, which are essentially the degree of resistance within a fluid to its own flow. And long story short, I won't get into the details too much of inelastic UV scattering, but we were able to excite the water bridge using a UV laser, and then to read back the shifted energy that comes out, a technique similar to Raman spectroscopy. And we were able to look at the image. Here's an image of the water bridge essentially using this technique. You see that there's an elastic scattering peak, which is what happens when the photons that go into the bridge are scattered backwards towards the source without changing their energy. And then we have Stokes and anti-Stokes lines, which essentially just mean that some interaction in the matter has either increased or decreased the energy of the photons. What this allows us to do is do two things. We can ask, does the speed of sound change in the water bridge compared to that of ordinary water? And essentially, it's maybe a little tricky to see, but those two red lines form a guide for your eye. And you can see that the bright tails, the Stokes and the anti-Stokes, are slightly inclined compared to those lines. What this tells us is that there is a sound velocity gradient. And we know that sound velocity is dependent upon bulk density. Bulk density, of course, is very easy to change with temperature. And so these curves are well known for liquid water, ordinary liquid water, as a function of temperature. And we do a fit, and what we find is that as we go through the bridge, R equals 0 being the outside of the bridge, R equals 1 being the inside of the bridge, we see that there's a temperature gradient in the bridge, a radial temperature distribution. Well, that's all fine and good. Okay, that's possibly not such a problem. It could also be a shift in density. Likewise, we have another piece of information that we can get from this image, and that essentially relates to the kinematic viscosity, the ability of the fluid to resist its own motion. And this we get by analyzing the width of those lines. When we do this again, at first we get a very nice linear fit, and then there's a lot more noise that creeps in. This is one of the biggest problems with studying the water bridge. As we saw, it oscillates, it changes its shape, it changes its size. This is always problematic in doing this kind of research. But again, we see that there's probably a temperature dependence or a density dependence. But actually, with this particular measurement, it can really only be a density change, because what we find is that the trend is the opposite in the other way. So again, a paradox arises. We cannot have a temperature gradient in both directions at the same time. So the only thing that can be happening is a density shift. So now it seems that we have two different densities in the bridge. And essentially, it's a decreasing density as you move from the inside of the bridge towards the outside of the bridge. We used another technique, neutron scattering, to be able to look and see now what's happening structurally. Are these water molecules behaving in a different way? Are they orienting in a different way than we typically find in liquid water? And so I really want to draw your attention first to that very large peak there. That's known as the first structural peak. It's the average oxygen-oxygen separation distance that you find for bulk, in this case D2O, heavy water. And we find that actually there's good agreement between the bulk and the bridge. So it says, well, we still have water. That's good, actually. We want the water bridge to stay water. After all, we want the water in our bodies to be water. Otherwise, we really have a very difficult time making good drinking water. But there's some interesting things going on here. This small feature at very, very, very low Q indicates perhaps that there's something strange going on. There's a shift in the microdensity. There's heterogeneity in the liquid. And this is something that's very problematic for scientists, because oftentimes when we treat liquids, we treat them as homogeneous isotropic media, meaning that no matter where you are in time or in space, you can assume that you will find the same character showing up again and again and again. And no matter which direction you move, it doesn't matter. So you're isotropic and you're homogeneous. Well, this begins to say, that's not the case. We've shifted this. We've created a heterogeneity. We've created directionality within a liquid. So one thought was, well, perhaps it's nanobubbles. Nanobubbles are the big hot topic these days. Everybody likes to think about them. And one of the easiest ways to find them is to use X-rays, because X-rays will find these nanobubbles because there's a symmetry loss across the boundary between the liquid phase and the gas phase. And this is preliminary data from Stanford, and I'm sorry you cannot see it, but it's a beautiful image of a diffraction beam from standard water, from bulk water. It looks just like this. This is actually from the bridge. And I fortunately have a nice little red outline to show you. But we see the first structural peak, which is a slightly brighter area, and inside, at low Q, where we would find a scattering peak for nanobubbles, there is none. So we know that there are no indications of static or stable nanobubbles in the bridge. So just to summarize, we know that there are changes in there's a radial gradient. There's a gradient in density within the bridge. And that this is not due to nanobubbles. But the question remains, is this just a water intrinsic phenomenon? Or do other materials, like other polar solvents, alcohols and whatnot, do this trick as well? Can we make an alcoholic bridge? Well, we tested a whole bunch of different liquids, and indeed we found that many of them do. It's very important that a liquid have a high dielectric permittivity, in other words, that it has some interaction with electric fields, and that it is also polar. It has the ability to align to those fields. It has a dipole moment, is what we like to say. But I want you to see that water is very different than most of these other fluids. Tetrahydrofuran, dichloromethane, acetone, propanols, yeah, they produce bridges, but they're far weaker, they're far more fragile, they're not as robust. Glycerol, however, is an interesting one. Glycerol is very viscous. So let's take a closer look at this glycerol. So here we see a glycerol bridge. And this video is nice because it shows you a phenomenon that we haven't shown you previously. And essentially, you can see that there are these oscillations that are occurring longitudinally across the bridge. This is something we see in water as well, but it's much, much faster. So, whereas we had to use a high-speed camera with water to visualize these things, with glycerol, we can watch in real time because its higher viscosity slows down the process a little bit. So we really see that this is a very dynamic process, and we see that there are density gradients moving within the bridge. So the structure of these bridges is very, very complex. Well, Lord Armstrong in 1893 was playing around with water bridges. A Frenchman, Polat, was playing around with other dielectric liquids in high current, high fields. And he was finding that a lot of these materials could do interesting tricks. And one of them was that they could change their height, the height of the capillary rise, if you will. Just like if you put a straw into water, it rises up the straw some way. He found that by varying the electric field, you could control the height of these liquids. And so we were curious to know if we could really reproduce some of his early works and produce essentially a liquid bridge that was just the bridge section. There's no reservoir attached to it. So a first attempt, maybe not so good. Let's increase the voltage a bit. You can see the tracer particles in there. Again, those polyamide tracer particles, so we can visualize flow. You see there's a lot of turbulence, a lot of things happening. And we pull it out. There we have a bridge all on its own. So we've now isolated the bridge structure from the reservoir. This, of course, is a very nice method because now we can just look at the bridge and not worry about the reservoirs. We are planning some experiments now to do these infrared measurements again on other liquids like glycerol. Just for comparison, I should warn you, if you have an allergy to math, you might not want to look at this slide. So what did Polat tell us? And why am I going down this strange little path here? He told us essentially that it's possible to substitute into the Bernoulli equation the electric field. And so you can predict the level of height rise. Scientists love to predict things because it makes us feel better about the world. We understand what's going on and we're not so worried about losing our tenure. But if we take a starting condition without an electric field and we have a liquid surface, we say the pressure between the electrodes and the pressure outside of the electrodes is the same. We apply an electric field, we get a height rise, and essentially what Polat told us was that we can substitute the Kelvin force, the acceleration force of the electric field, for a pressure gradient. So just like Bernoulli, you could change the pressure on a liquid and you can push it up. This is how we drink through a straw, essentially. We reduce the pressure over the straw and the liquid rises into our mouth. And we can put it into the equation, the Bernoulli equation, substituting in that mass section there. Instead of pressure changes, we put in the electric field, dielectric permittivity, rearrange it a bit, and we can predict the height of the bridge, and actually it works very well for all of these liquids. So all is well in the world, except for when we started to look in the infrared. So if we look at two bridges, here's one propanol, two propanol. You see that they're more or less the same. But when we look in the infrared, we see that they're not. This was problematic for us. Suddenly we're like, this is a bit strange. One propanol and two propanol have very, very similar boiling points, vapor pressures, dielectric permittivities, viscosities. Their physical properties are almost identical. But when I look at a one propanol bridge, I see that it's warm. When I look at a two propanol bridge, I see that it's cold. And so I really started to wonder, why is this? Why is this happening? Well, one of the most important factors in heat generation are free ions. And Onsager, this is 1936, somewhere around there, basically found that the stability of free ions is dependent upon the structure of the molecule. So in one propanol, we have a primary alcohol, which, to go back to basic high school chemistry, means that that you have your chain of carbon atoms, 1, 2, 3, and then the alcohol hanging off the end. Whereas in 2-propanol, you have the alcohol in the middle of the molecule. Now, primary alcohols are actually much more stable in their ionized form than secondary alcohols. This is just because of the way that the orbitals are hybridized, the electrons are much more easily shared, and so as a result, when you ionize a primary alcohol, it stays an ion. What is the point of this? Essentially what it's telling us is that the molecular properties of the species present in the bridge determine the bulk behavior of the bridge. This is very important. This is telling us that we cannot just consider a material as a large ensemble, but we must look more deeply into the microscopic structure. So, to conclude, we know that the water bridge essentially has shown us a new state of liquid water. And it's an electrically controlled state, something we can turn on and turn off. Furthermore, this state is not just field dependent, but it's also dependent upon the flow of current. And this is something that we are actively right now exploring as to why that is the case. We know that there's a gradient in the velocity of sound and the kinematic viscosity, and that both of these indicate a change in the bulk density properties of liquid water. There's a gradient in the bulk density from the outside of the bridge to the inside of the bridge, meaning there's a morphology, there's a structure, and it's a structure within a liquid, and that we cannot consider liquids anymore to be isotropic and homogeneous. And furthermore, that these bridges are not water intrinsic, but unique in water is a robustness and properties which are key to biology. So I'd like to thank you all for your attention, and hopefully there are some questions. Yes, and thank you, of course, for your attention. And thanks to all of our supporters and collaborators. Actually, this work has taken quite a few different people and experts from many, many different fields. So